see that recording later, right? So this video is recorded as well
Yes,
as
sir.
you have.
That's very good, sir.
Uh, yeah, you already have agreed to that before as well, because that's also for our own ease, because you never know when there is a breakdown in Karachi. Okay, so there are two people more, Mohammad Fahd Khan and Altaf Ali Shah Rizvi. So please, both of you, can you unmute yourself? Can you turn on your mics?
Yes, sir.
Say, Altaf Ali Shah, how are you?
Sir, fine. How about you?
Alhamdulillah. So what are you doing, Altaf sir? Any job right
Sir,
now?
nothing, sir. No, sir, nothing.
Okay. So when did you complete your masters, your undergraduate, and from
Sir,
where?
2017.
Mehran University.
Mehran
So
University, Jamshedpur.
you're currently in Karachi, or you're not here?
No, no, internet side, sir. Tandwala.
Okay. So how good is your internet connection or your bandwidth? It's fine. Okay. So I don't have any
Yeah, fine.
problem if you can
Internet
open your
fine.
video as well. It's okay for me. It's better if you open the video so that we can see each other. And then there is Mohammad Fahd Khan. Yes, Mohammad. Hello. Your voice is a little low, Fahd.
Can you hear me correctly now?
Yeah, yeah, yeah. That's too good.
Assalamu alaikum.
Walaikum assalam. Okay. So Fahad, what are you doing right now?
Sir, I am an assistant manager in Cybernet in the Network Operations Center.
Okay. And what are your core responsibilities there?
My core responsibilities are to manage the network, the whole core network of Pakistan for Cybernet,
Okay.
as it is an IS internet service provider. So
Right.
therefore, I'm mainly the operational stuff of all the networks, the whole what do you say that the nationwide network. We are managing that.
Okay. Okay. Good. So we have got four people now, and there are four more, but they have not joined. So let's start it, because this is our first lecture, and obviously it's all about you people. If you are going to find it easy in this way, we can do it this way. But if you find it a little difficult, and you want to have a different way of taking the classes, because as I've mentioned, that in undergraduate we go with both offline and online courses. Here we are just going for online lectures. So if it's okay for you, then we can continue with that. But if you want that there should be some material before the class starts, I can do that as well. Okay, so if you want to unmute, you can unmute yourselves. You want to mute that because of some other because you people are at home, and then you can have different voices coming from the background. You can also mute yourself. So, but I'll be asking some questions. So at that point of time, you can unmute yourself. Okay.
Yes, sir. Fair enough.
Okay, sir. Fine, sir.
Okay. So I'm going to present now, and I'm going to start with the presentation. Okay, is the presentation visible to all of you?
Yes,
Yes,
sir.
sir.
Okay, good. So this is our first lecture, right? And yeah, these will be our topic here. So today we are just going to go with an introduction, just basic introduction of computer architecture, right? And what we understand by that, some common terms, some terms that you have studied earlier as well. So that's going to be just an overview for today. Then we have computer arithmetic. So this topic comprises how the ALU works, Um, so when we are discussing about the internals of computer, we have three and four common components. One of them is the ALU that performs the main data processing. So we are going to discuss the different techniques here, like what are efficient adders, how are multipliers and dividers going to work, what are floating point numbers, and what is floating point arithmetic, how can we use different schemes to improve their performance. All these topics are going to be covered in under topic of computer arithmetic. Then we are going to come to that instruction level parallelism by the sixth lecture, something like sixth or seventh lecture. In instruction level parallelism, it's a technique to improve the performance by using by overlapping instruction executions. So you must have studied pipelining in your undergraduate courses as well. So instruction level parallelism is more about pipelining and what are the difficulties in pipelining the processor, the internals, the steps. We are going to discuss about that by the sixth lecture. Then normally what happens is by the end of instruction level parallelism topic, we have a midterm. I'm not sure about what's going to happen in this semester, but normally that comes about around the ninth semester, and we have a midterm. And after the midterm, we go for the memory topic. So memory organization, what are caches, how are caches optimized. So all these topics are then covered later. Then we have topic on data parallelism. Here we discuss about vector processors, and we also discuss about the later GPUs and SIMD extensions of Intel. So that's about data level parallelism. And then in the end, we also discuss some recent architectures. What are the different architectures like RISC-V and others that are implemented these days. So and these recent architectures would be discussed along with every topic as well. So it's not necessary that we have this as a separate topic. We are going to discuss with everything some recent works that are being performed. Right. So the books here, the book is Computer Architecture by Hennessy and Peterson. That's the book that we are going to follow. The book is titled Computer Architecture: Quantitative Approach. We have the fifth edition easily available in the market and also available on the net. If you want to download that, you can find that. Although it's not correct to download that version, but it's easily available on the internet. But it's I would prefer you have this book, or you can use the library service whenever the library opens. So it's not open right now. So the sixth edition is not currently in Pakistan. It was published in 2018, but I had been looking after that, and all these publishers here, all these bookstores here in Karachi or even in Pakistan that provide online, so they don't have this copy of 2018. But luckily, I could find one version of that from one place. So, but we are going to follow with the fifth edition. Okay, so it's not a problem. You can use any one of them. And then for the computer arithmetic topic, we are going to go with Behrouz Parhami's book. Again, there are two different editions. The first edition is available in the library, the NED library. The second edition could be there. I'm not sure. I have not seen that edition yet, but it's available, right? So it's a very good book on computer arithmetic. Gives a very good insight on how the arithmetic algorithms work, right? And then we have for reference advanced computer architecture. Again, it won't be necessary unless you want to go into detail and see how things work, right? Okay, so let's come to the grading part here. So again, last time we had grades. We didn't have grades in the last semester, but out of those 100 marks, um, all the grades like satisfactory or incomplete were decided on the sessionals. I'm not sure what's going to happen, but I hope that things are going to get better by August. And probably for master students, we can have master students coming to the university with social distancing, right? So if that's possible, then our ninth lecture would be on 20th of August, and that would be our midterm. So if everything goes fine, we can have a midterm on 20th August. So midterm will have 20% marks. That's normally what I do in all these course in all the computer architecture courses that I've taken before. But things could be a little different in this one because it's an online one. So I won't be forcing students to do uh, a lot of stuff. So I'll be taking some small quizzes, and maybe the quiz percentage would go up. So it's 20% for midterm and 10% for quizzes, but it can go 15% for both of them as well. So quizzes means small quizzes, like we are going to discuss one lecture, and probably the next day or maybe at the end of that lecture, a small 5-minute quiz to just check what have you understood. So class participation also important. If you are going to ask questions, if you're going to participate, it's going to increase your marks. And there could be some assignments as well, assignments related to the book. So this is about the grading here. Now let's come to our main topic. So the first thing that we are going to do is go through the computers and the types of computers and the classes of computers. Now, computers have different types, and depending on their types, they have different needs, and their emphasis is also a little different. Now, the first class of computers we are going to discuss are personal mobile devices, or in short, we call them as mobile phones or tablet PCs, right? So, in terms of revenues, this has now become the highest or the largest market, right? So before 2016, around that, laptops were the most one to be sold, but then afterwards, the personal mobile devices were more throughout the world. They were the largest. They had the largest market in terms of revenues in among all those computers. So what is a personal mobile device? It's basically a web-based or media. It runs basically media-oriented applications. The main thing here is you don't have unlimited power supply, right? So it's battery powered, and then you don't have any facility for cooling it, so you need to design it in such a way that there is no heat generated that can destroy the devices. So you have to deliberately design in such a way that it cannot do much high computation works, so because there is nothing for cooling, and also because it's battery powered. The emphasis for personal mobile devices is on energy efficiency, right? So the more energy efficient, the better it is. And obviously the size as well. So it includes both the code size and the hardware, because the memory is also restricted. And we are also going to talk about the emphasis here on cost, because people like to have these personal mobile devices with a lower cost. So you don't go with for expensive things like metal casings or something like that. So less expensive packaging is going to be used mostly. This is also because it doesn't it gets heat up a lot. So you have restricted the heat profile there, and then you can use less expensive packaging materials. So the cost is also important here when designing these classes, these class of computers. Okay, so the task here is the emphasis here is on responsiveness. That is, the real time constraints here are soft. So when we're talking about real time constraint, there are two types of constraints in a real time constraints: those that have soft deadlines and those that have hard deadlines. Now, when you talk about soft deadlines or soft real time systems, that means that if you miss that deadline, it's not going to create any harm to the environment or the user. So for example, if you are running a video and the processor is decoding it, and with because the processor is slow, it misses one of the frame, which may cause a little delay in the video. But so it has missed the deadline of processing that frame, but that constraint would be called as a soft constraint, soft real-time constraint. On the other hand, if for example you are driving a car and you have a system which has to process it in a particular time duration, again there is a deadline, but if you miss that deadline, that can be catastrophic. So there are two differences here. So soft deadlines means that if you miss them, it's not going to cause harm to the user or the environment. But so when you're talking about mobile devices, they are basically built for responsiveness, but their time constraint is soft, right? Again, along with cost, there is a weight constraint here. So these are the emphasis of the personal mobile devices. So this is our first class of computer, right? So computer obviously is anything that can process data. So this is also a computer, a class of computer. So why are we studying classes of computer? We need to understand what each class demands, right? So what is the emphasis of each class and how do you want to design them? For example, if you're just concentrating on mobile devices, you are seeing that there is no fan for cooling. So this means you have to limit yourself to a particular frequency of processing. So this means that you cannot go for very high computational programs, very compute intensive programs. So this means that, for example, if you are designing a system which needs say 3 or 4 levels of memory, you're going to say that no, personal mobile devices, they don't have unlimited amount of memory, so I cannot have a memory system which can have 3 or 4 levels of caches. So let's just go for 2 levels of caches because I'm limited with my power supply. So for every class of computer, there is an emphasis on what that computer does, right? And depending on that, we are going to design that thing. And that's the whole topic, the main concern of this course, right? So to understand what are the different details of these computers and how do we work with them. Okay, so this was our first class. The second is a desktop computer, and both desktop and laptops are included in this category. So it has got the second largest market in terms of revenue, not the first one, right? So when we are talking about mobile devices and you want to compare two mobile devices, there is no benchmark program that can easily say that this mobile is better than the other one. But when you're talking about laptops or desktop computers, there are well-defined applications and benchmarkings programs, so you can run program on two PCs and see which one has performed better, right? Okay, so their emphasis is obviously different than mobile devices. Here we are talking about performance, right? So the main issue here is performance. So if it's not going to perform well, you're not going to buy a desktop computer. So the main emphasis of desktop computers is not about multimedia, it's not about users responsiveness, it's about performance. The other thing is cost. So again, cost is obviously going to be there for all classes of computer. So again, the cost matters here. So if you are getting two different computers having a performance, there is always going to be more cost for a higher performance computer. But then we go for a price performance combination. Like for example, if there are two computers, and one of them is better than the other, but it's also higher cost, and the cost is say twice higher than the other one, but the performance is just 1.2 times higher than the one. So you don't go for just the performance, you go for a price performance combination. What performance am I getting for that particular price, right? So the emphasis of this class is also on this combination, the price performance combination. Again, response time is important here because users are going to interact with them. So they need high responsive systems. So you can see here, there is no emphasis on energy, right? Or power. You're not concerned with power because you know you have got unlimited amount of power. So you're just going to connect that from an AC supply switch and then you can get unlimited amount of powers, or even for a battery, there would be some connections for that can connect you to an unlimited amount of power. So in these classes of computer, your main concern is not conservation of energy. You are not concerned with building these computers, considering that applications consume less amount of energy. You are building them for performance, right? So that's the main difference between these two classes. And if you are going to compare them, so this is a graph showing you in terms of revenue worldwide, how many systems have been distributed, how many systems have been um, uh, sold throughout the world. And you can see here that this graph here on the top is about this one here, this blue line is about desktop computers. So if I go to 2010, for example, I would see here that it was all about desktop computers at that time, right? This green graph here is about mobile devices. So we people had different types of mobile devices, and obviously they were quite cheap at that point of time, and they couldn't do much work. So they were the older versions, and they were just built mainly for communication, not for accessing multimedia application. But later on, there were different devices, and different applications could run on them. Starting from 2011, there were different Android devices that were included. And then you see on that the in terms of revenue, the mobile devices graph is growing, right? Until we come to 2019, where there is a little downward peak and an upward peak for laptops. So, but again, you can see that things are again higher for the laptops, for the mobile devices than for the laptops. The bottom here is the tablet. So tablets, the graph here shows tablets from 2012. Before that, they were considered as part of console systems. So they are just including them from 2012 year. So what you can see here is that the trend is that the mobile devices are growing in the market. So people are more interested in mobile devices than laptops, right? Although what you're going to see in this whole diagram is, due to online classes, people are buying more laptops these days than mobile devices, right? And if you go to market, you're not going to find any more laptop, any older laptop or any new laptop on the stores. Yes, there is. Is there any question here, Mohammad Fahad Khan?
Sir, I would like to ask you that was there any kind of such event, just like you mentioned, that nowadays there are a lot of people who are buying laptops rather than mobile phones for online classes. So
Mhm.
the peak which at about 2018, the last quarter of 2018, there is a little spike in the desktop systems.
Yeah.
So was there any significant event that caused this?
I'm not sure about that, but I haven't read any specific event for that. But the thing is, these desktop computers are also used. So, where do you think is the biggest market of desktop computer these days?
The biggest market probably, uh, if I would to consider my situation, there are more gaming
Yeah.
PCs that are being sold nowadays rather
Right,
than
right,
the
right,
mobile
right,
phones.
right. So when you're talking about desktop computers or laptop, there are two main reasons for buying them, and one of them is, if you want to run a program that has got high computation power, like for example, you want to code something, you want to program something, you need to be a computer scientist for that. So you need to be a computer programmer for that, right? So if you are in this field, then you are probably going to work on PC, right, or a laptop. Other than that, the main market these days is gaming, right? So gaming systems are obviously PC based system because they need high performance, right? So you cannot run the same game on the mobile devices. So this is one thing where they are mostly used. The other thing is when you talk about combining these to form a cluster of computers. Sometimes what happen is when you are going to for warehouse scale computing, you buy a lot of desktop computers and combine them through these switches, through the network, and then you also need a lot of these desktop computers, right? So I'm not aware of any particular event that happened in 2019, but there was a little spike here that shows that laptops were sold more than the mobile
So can
devices.
I add one thing?
Sir, it might be a freelancing boom. Recent
Sir, can I?
times,
Uh,
freelancer are increasing.
Could
Yes,
be
Mohammed
possible. Could be
Jaz
possible.
here,
But
sir.
freelancing was always there. Freelancing and gaming was always there.
I had a hunch about probably the advent of AI,
The
artificial intelligence,
No, again, artificial intelligence was also
because
there before that as well. And when you're talking about when you're talking about training systems, those programs were running before that as well. So there is a boom over there. But these days, people are using specialized devices for training their systems. So they are not using the laptops for training networks, the artificial networks. So what they are doing is they are building systems on say dedicated hardware units like GPUs or TPUs. So again, there is another class here. So they are building the systems on smaller devices and which are more say tuned for training applications. So but artificial intelligence was also there before that. So the training was happening before that as well. The artificial intelligence got its boom starting from again 2014 15, and people were more in this field, machine learning field. They were doing the task before that as well, from 1990s as well, but because of some hardware constraints, people were because of those hardware constraints, AI was a little, you can say, people could not implement their algorithms properly. So, but because of these high advanced machines these days, they can train their system, they can build their networks, which are more complicated and give better results. But okay, so what I can do is, or you can do as well, is go for why this there was a peak over here. And so again, there is a this is kind of a quarterly report, but still, maybe it looks as if it happened in some particular month. That's the end of 2018 and the beginning of 2019. So I'm not
yeah.
sure.
So
It's
we'll have a look. We'll have a look and we'll discuss it.
okay. Okay, right. Thank you. So these stats are available online as well. So you can go to Stats Counter and you can develop your own stats as well. So you can find what is the revenue worldwide or within Pakistan or within any particular country. Okay, right. So let's move on. So this graph shows here what are different trends in these two. Then the third class of computer are servers, right? So when you're talking about servers, again, they are large scales and they are designed for computing services, right? Their emphasis is on availability, right? So you need those servers to be operational for all times. When you're designing desktop systems or mobile devices, you are running applications which are not going to run for all times, or you can say in such a way that if they are closed, it doesn't matter for a particular duration. But when you're running something on a server, it's highly important for you, and you don't want that server to be closed at any point of time. So when you're going to design servers, you're going to design the memory system and the ALUs and the other things, keeping this in mind that it's not going to be ever closed, right? So you have to have a very efficient cooling here. You have to design it with by considering that, for example, if a memory gets corrupted, there should be some mechanism to share the contents with some other memory. There should be some RAID system they have developed. You need to have you need to have a design in which you can easily change a particular unit with another unit, right? So if there are multiple disks and one of the disks is needs to be replaced, it can simply be taken out and a new can be inserted in without closing that system, right? So these are the more emphasis. These are the things that are more important in a server. So we need availability, we need scalability, right? So whenever you're going to design a server, you are considering that this is say a particular year, but after 5 years, we need to have more of RAMs in it, more of hard disk in it, more of other things in it. So it should be scalable. So you can easily add more things to it without disturbing its configuration, right? So as mentioned, that as demand increase, there should be no problem in improving that. And the emphasis is not on responsiveness. So this is a little different than the previous two classes, where we were talking about users directly interacting with them, and they were more concerned about their own program and how responsive that program is. Here, our target is not responsiveness. Here, our target is throughput. So what is throughput? When we talk about throughput, it's how many tasks have been completed in a particular time. So it's not about individual tasks, it's about a collection of tasks. So for example, if you're running something on a desktop, you have program A and program B. So you want to figure out how much time is program A going to take, and you just note that down and you say, okay, my program A takes this much time. But in a server, you are not going to be concerned with just one program like program A. You are going to talk about, say, running hundreds or thousands of programs together and seeing how well is your system working, how well are these programs completing, right? So we are not talking about individual program here. We are talking about how many tasks have been completed in a unit time, right? So the main concern is in servers is availability, scalability, and throughput. Then there is another class of computer which is more common these days. It's cluster or warehouse scale computers. It's the main thing that is driving the cloud systems. And here we are using it's kind of something like it's a warehouse size of computer, right? It's not necessary. It's not necessary. It is at one place. It can be at different physical locations as well, all working as a single computer. And you never know which particular part is going to give you the result because they are all interacting, and there is a very efficient software which is going to share the load between these different modules. So we are talking about hundreds and thousands of desktop computers here or servers that are connected together to form one big warehouse scale computer, and that is going to perform that is going to give the result in very short time. And again, that the emphasis is not of single result, but there are going to be multiple requests coming and millions of requests coming per second, and then these computers are going to address that, right? So when you have tens and thousands of these together, then everything matters. For example, if you are getting two desktop computers with similar performance, but one is of, say, for example, in terms of rupees, for example, 90,000, another is of 100,000. So even you are saving 10,000, but since you are using 10 or thousands of them, so this means 10,000 from each of them means a lot of money, right? So the emphasis here is again availability. You need those servers to be operational all the time. These warehouse scale computers to be operational all the time, and the price. As I mentioned, that even a small price saving is going to affect on the overall price. And obviously here performance matter, right? So the performance is going to matter here because the main task here is again that we are talking about how many users have been satisfied. And right, power. So power was not a concern in desktop and power was not a concern in servers, but here power is going to be a concern because we are using 10,000s of these together. So if there are different ratings of power for a particular desktop and you are using 10,000 of them together, then this means that overall performance, overall power can go very high or very low, right? So power can be a main factor here. So you need cooling as well for these systems. and the cooling takes a lot of power. So there are electricity costs as well. There are power bills as well. So but these systems obviously take their money from different other sources, like for example they sell their services, or they get them from advertising. So they run their system on this model. And obviously, since all of that is connected through internet, so the internet bandwidth is also concerned over here, which is never in any of the previous classes here. So you have to have an efficient software as well, which is going to handle the load sharing. Okay, a subclass of that is supercomputer. An earlier supercomputer can be included in as a subclass, but when you're talking about supercomputers, basically you don't connect them through an internet connection. You connect it by an internal network. So they are very high performance networks, interconnection networks, to connect these different processors in a supercomputer, so it gets better performance. And it's always at a localized place, right? But it could be called as a subclass of this class of warehouse scale computer or clusters, right? Then our fifth class is embedded computers. Now, this is a very different class of computer, and many people don't consider that even as a computer. But this is also a computer because it's also going to process data, and you can write your programs on that. So these embedded computers, you can find them at many places, right? For example, cars, trains, microwaves, air conditioners, different medical equipment. So they are a variety of types. So for example, you can have um, you can go for a very small kind of embedded device to a very sophisticated device as well. So all of these systems are different than PMDs or mobile devices in just one way. When we're talking about a mobile device, we say that they can run multiple softwares together. But when you're talking about embedded computers, they are designed for one purpose, right? And they can just do one task. For example, if you have an embedded system in a washing machine that can uh, measure the weight of your clothes and decide on the weight, it can fill the water, and then it can do different tasks. Programs can run to wash those clothes. This is just one task, right? So you cannot play games on a washing machine, right? So washing machine system is built for a particular task, right? So that's called as an embedded computer. So it's embedded in a bigger thing. So that's why it's called as an embedded computer, a larger product. But when you're talking about mobile devices, it's not necessary that you run one task. You can have games in that, you can call through that, you can run different multimedia applications on that. So again, mobile devices are a type of embedded computers, but we differentiate them in this way that embedded computers do just one task and they are built for one system, while mobile devices can run different other softwares, and they are more related to the desktop version of computers. Okay, so when you're talking about embedded computers, is a big variety. These can be implemented using general purpose processors or special purpose processors or single purpose processors. Like I said, that if you are going to design, if you are going to have an application in mind, for example, you want to do signal processing, right? And for signal processing, your main task is just to process the signal and to say denoise something. So you are going to use a DSP processor. So that's a dedicated processor for that. And you're going to build an application into a mic, for example, which is going to automatically cancel the noise, right? So that's going to be called as an embedded computer. So it's still going to be a computer, right? Uh, so they have a wide variety of them. The emphasis again here is on power and energy because they are mostly remote and mobile. So power is mostly battery powered, and the emphasis again is on cost as well. So cost is going to be there in most of the computers that we have seen. The size is important here because it has to be fit into a bigger product. So the size matter. You cannot use unlimited amount of memory, uh, or you cannot have a bigger battery over there. right? So size is important because it has to fit in a bigger product, and the weight obviously is also matters here. The performance is the concern here, and the real-time constraints are both hard and soft. So if you're driving a car and you have a system where you have so there are different embedded systems in computers. So one of them could be an ABS, for example, anti-lock braking system, and the other could be your airbag system, where it's going to just detect that if the car decelerates at a particular rate which is higher than allowable, then it's going to quickly initiate the process of inflating the airbags. Now, inflating the airbags is a chemical process. A chemical interacts and blows the air into those sacs, and then it takes some amount of time, right? So it has got a very short deadline to decide whether the car is going to go for an accident or that is not an accident, right? So for example, if the time duration is say 25 milliseconds, right? So you have to build a system that can react in 25 milliseconds. So it has to be a system which can calculate all those parameters and equations that is going to determine the deceleration of the car within 25 milliseconds and start the process. And because it's a chemical process, it has to react in a efficient way. It's going to take some time. You cannot change that time. So you have to decide everything into mind and build a system. So you're going to set a deadline, and that deadline would be called as a hard deadline, because if you miss that deadline, then it's going to cause harm for the system, for the environment, or for the user, right? So it's not a soft deadline in this case if you're using it in a car, right? Maybe for some cases it can be a soft deadline, because like the example that I gave, that if you're building a system which is going to decode something, a video decoder. So if it misses some frame, there would be some jittering effects, but it's not going to cause harm, right? So in embedded system, you can have both hard and soft deadlines, but mostly it's going to be hard deadline, right? So you're going to see this class is the most used computer. So for example, if you're talking about calculators, uh, they are a class of computer as well, right? And what that class is, it's an embedded computer, right? If you're talking about say projectors, again, that's also an example of an embedded computer. If you're talking about an AC system running in your room, which detects the temperature and selects the ambient temperature, and then tries to control the fan speed and everything to make the room environment better. So all of that needs some different sensors. So it's getting inputs from different sensors and working on it. So these are the different 5 classes of computer, and every one of them has different emphasis. So we are going to just I'm going to just stop over here for some questions from your side, if there are any. Yes, anyone? So when we're talking about different classes of computer, there are different emphasis, and so this is the main thing that we have to study here in this course. Like for example, what is the relationship of a memory system with a particular class of computer? So if you're building a memory system for a server, that would be a totally different memory system, right? And if you're building a memory system for a personal mobile device, PMDs, that would be a totally different system, right? So there are different constraints, the different options there. So the first thing that you have to consider is what are the different computers there in the market and what are their needs. Okay. So if there are no further questions, because because this is something that everyone knows here, so I'm just going to continue. Right. So now let's come to computer architecture, the main point, the main term used in our course, advanced computer system architecture. So when you talk about a computer architecture, the older view of computer architecture was that it's all about instruction set design. So when in earlier days computers were built, the main target or of an efficient computer was how good is the instruction set, how many instructions are there, what can those instructions do, right? And depending on those instructions, you build the whole system, you build the organization of the of the circuit, you build the internals. Like for example, if there is a multiply instruction, you have to build a multiplier. If there is no multiply instruction, you have to do that through, say, adding or shifting. So it was mostly about just the instruction set design. So, and then depending on that, there were other decisions that were made. But that was an older view of computer architecture. Now, when you're talking about computer architecture, it's more than that. It's more than that, because as Mia mentioned, there are different classes of computer, and everyone has a different emphasis. So when you're talking about the computer architecture, the design, the task of an architect here is to determine the different attributes important for that particular class of computer, right? And design it to maximize the performance and the energy efficiency, considering the cost, power, and the size constraints. So it's not only the instruction set architecture, you're also talking about the packaging, you're also talking about the cooling, you're also talking about the IC design, what particular IC design is suitable for this class. For example, if you're going to decrease the feature size, it's going to be good, but it's going to be more costly as well. So if you're designing it, if you're making it for a mobile device, and it's going to cost, say, something like 500,000 rupees, so no one is going to take that, right? So it's all the task of a computer designer to know that what system is built and for what purpose is it built, and depending on that, he or she has to take decision whether or not to include a particular memory, or to include a particular instruction, or to include a particular packaging, right? So all of that is part of computer architecture. Now, before we move further, we are going to discuss about the trends in technology over the past years. What are the different technologies that have been used? So the electronic side, so the first thing that we are going to discuss is the IC technology. Now, when you're talking about the IC technology, the transistor density has increased by 35% per year, right? The die size has increased about 10 to 20% per year, and the combined, if you combine both of them, the overall growth rate of transistor count on a chip is roughly 40 to 50% per year. So this means that it's going to double every 24 months, every 2 years, right? So this is also sometimes called the Moore's law. So it wasn't a law. Moore's was a computer scientist way back in 1960s. He predicted that depending on the trends that he saw at that particular time, he saw that the IC technology, or the amount of transistors that can be built into a chip, is increasing at a rate of double every 2 years. 50% every 2 years, right? So it's not double. The growth rate was 50% every 2 years. So for example, so what happened was, when that thing came to the semiconductor industry, they took it as a target. They took it as a target, and they said that, okay, so we are going to use that, and this is the milestone that we have to achieve. So what they did was, they tried to follow that from that time onwards till now, right? So what's happening is that you can have 50% growth rate of transistors on the same chip size, right? And this is allowing you to have more transistors on a chip, which means that more devices can fit in, more logic can fit in, more units can fit in. So instead of having one core, you can have multiple core. You can have the whole memory designed into a chip. You can have multiple levels of memory designed to chip. So you can give different ideas here. So because the transistor technology has improved, the transistor density has improved, and the die size has also increased, right? So that was later on called as the Moore law. So it was something like stable. But these days it's getting a little difficult to follow it anymore because of the other restrictions, the physical constraints. There are physical constraints because when you're building a transistor on a chip, It's mostly an optical process where you mask you apply a mask and you etch for a transistor, and you apply that through the available wavelengths that you have. But again, there is a restriction, a physical constraint, that you cannot go beyond a particular wavelength, and that has reached its limit these days. So you cannot have more of that transistor density increasing per year. It's going to be a flattening. It's somehow going to then stop as well, because so they are coming up with different techniques, and still they are going for lower feature sizes. But yeah, it's getting a little difficult. When you're talking about DRAM capacity, now DRAMs are the main memories for the laptops here. The use is because they are faster. So DRAM uses a capacitor-based technique, but that's not the same capacitor as an integrated capacitor. That's a semiconductor capacitor. So when you design a MOSFET, there is a capacitance there, and that capacitance can be used for storing a 0 or a 1. But that quickly the capacitance can quickly the charge can quickly finish. So what you can do is you have to refresh it. So when you're talking about DRAMs, they are faster, but they need also a refresh cycle. So, but the problem here is that again, to build a capacitor, it has to be a particular size. So you cannot have more. So that size cannot be reduced. So the capacity is slowing, and is doubling around 2 to 3 years, and probably is going to stop because you cannot have much smaller capacitors to store the charge. So the other memory that is used these days is flash memory, and that memory is more popular these days, and it's a little slower than that, but since it is cheaper, and it has other benefits because you don't need to refresh it. So it's used mostly in personal mobile devices and desktop computers these days as well. Okay, so the other memory technology is the magnetic disk technology. It's optical disks, or so tape drives are no more used, but optical disks are still there. If you're talking about server systems, they are very cheap but also very slow, right? And this technology has also increased by 40% per year, right? But again, there are certain limits here. So except for flash capacity, which is improving, the rest of them are slowing down. Okay, if you are going to consider the throughput versus latency graph, so first of all, what is bandwidth or throughput? When you're talking about different processors or networks and memory, you talk about their bandwidth or throughput and the latency. So throughput is how much tasks is completed per unit time. Latency is how much time is an individual task going to take, right? So so say if I give an assignment to a student, and there is a single pen to complete the assignment. So if say this class has got 1, 2, 3, 4, 5 students, right? So there is a single pen, and everyone has their own paper, but there is a single pen. So what happens is the first student in my list is Akash Ali. So Akash Ali completes his assignment, then he gives the pen to Hail Saeed Haider, and when he completes, he gives the pen to Mohammad Imtiaz, and so on, right? So what happens in such a scenario? So everyone has a paper, but there is a single pen. So and everyone has their own writing speed. So the bandwidth is how much tasks have been completed in a unit time. So if I say that Akash takes about an hour to complete, and everyone takes about an hour to complete. So there are 5 students. So if I want to ask how many tasks have been completed in 3 hours, I'm going to get an answer 3, right? Because in 3 hours, everyone taking 1 hour, so everyone is going to complete in 1 hour. And then since there is a single pen, so it's going to take 3 hours to complete 3 tasks, right? So how many tasks are going to complete in 3 hours? So it's only going to 3. Now, if say we have now 2 pens. Now, if we have got 2 pens, so what is going to happen is 2 people can start their work at the same time, right? So, for example, Akash Ali and Hail Saeed Haider can start together, and Imtiaz, and after they finish, so Imtiaz and Fahad can start their tasks together. So, if I ask how many tasks have been completed in 3 hours, so because there are just 5 students, so I'll get the answer all the 5 students have completed the task in 3 hours, right? So what is this? This is about bandwidth. This is about how many tasks can be completed in a particular unit of time. So we are always going to talk about a time first here. So how much improvement is going to happen? It is obviously depend on how you can improve the bandwidth or the throughput. So for different terminologies, we use the word bandwidth, and for the other one, we use the throughput. Basically, the same idea: how much work is done in a given unit time. Now, when you talk about latency, it's actually how long does a single task take, right? Now, let's just go back to our previous example where we had a single pen. So everyone was taking 1 hour. Now, if, for example, Akash Ali improves his speed and completes that in 40 minutes, and Hal Saeed Haider also completes that in 40 minutes, and Mohammed Imtiaz also completes in 40 minutes. Now, when you're talking about individual tasks completing earlier, you are talking about the layer latency or the response time of a task. So if I now talk about how many tasks are going to complete in 3 hours, so there are 5 students and each taking 40 minutes, that would mean how much? 5 into 40? That would be something like 200 minutes, or 200 minutes would be yeah, it would be still a little bigger
30
than
minutes, 30.
180. Yeah, so it's still going to be bigger than 3 hours. So one of the students, so 4 tasks are going to complete, but instead of 3 hours, one more task is going to complete, right? So we see here more tasks can be completed if we improve the latency as well, right? So if everyone improve its speed with a single pen, still you are going to get a better performance. So both latency and bandwidth can be improved. But what do you think? Which of these two is easier to improve the performance, bandwidth or latency?
The individual performance, obviously, sir, latency.
No, what I mean is if I have something to improve, a performance to improve, uh, the performance is going to improve if I improve the bandwidth. The performance is going to improve if I improve the latency, right? So my question is, which of these two do you think is much easier to achieve? Either bandwidth or the latency?
Sir, it would depend upon the system we are working on.
Okay, so yeah, if I talk about the network, the systems that are available here, what do you think? For example, let's talk about say hard disk or memory. So let's talk about the memory. So memory, you apply an address and you get the data, right? So it takes about, say, let's say it takes about 100 nanoseconds for that operation, right? So that's the latency. If you try to improve that, so that's the latency of one word. Now, if I want to fetch, say, 16 words together, so I'm going to multiply 16 by 100 nanoseconds to get the overall time for my whole fetch operation, right? Now, one way to improve performance is that I reduce that time for individual tasks. So instead of 100 nanoseconds, each task say takes about 80 nanoseconds. So now I'll going to multiply 16 by 80 nanoseconds and I'll get a time, and that would be the time that I finish, right? So that's one thing. That's about improving the latency. But bandwidth, so, or throughput. So what if I have 16 different memories and I spread out my data in such a way that every memory gets a particular byte, and when I get the address, I apply the address in parallel to all of them. So even if they take 100 nanoseconds, my result of 16 bytes is going to come in 100 nanoseconds, right? So what is needed over here is I need 16 different memories. Obviously, it's a bigger cost, right? So when I'm talking about pens, if there are multiple pens, you need bigger cost to do that. But the thing is that it's much easier to do it, right? It's much easier to do it because if you have enough cost, you can replicate it. Then you're going to see that improving bandwidth is much easier to do than improving latency, because latency has you can say you come to a point where you cannot do anything more, right? So you are then going to limit yourself, and then you can do nothing more to improve that. For example, like in this case of memory access, so address has to be decoded, then the memory has to be searched for that particular location, and then it's going to put the data on the data lines. So everything has some delay. So if you want to improve individual delays, there is a limit to what you can do, and then you're going to stop. But if you want to improve the bandwidth, you can have different choices for that. You can have multiple memories working in parallel. So parallelism is one thing that can improve bandwidth very easily, right? So when you see this graph over here, this graph shows the throughput and latencies together. So this is a log graph. So you can see here at the x-axis is relative latency improvement, right? And sorry, and on the y-axis you see relative bandwidth improvement, right? So let's take one thing here. Let's take disk. So if you're talking about disk, so you're going to see that this line here, that this is a straight line, this is a linear one. So had latency and bandwidth improved at the same rate, you would have obtained this particular line, right? So if you get any line which is on the upper side, this means that the bandwidth has improved more than the latency. Okay, so if you talk about disk, you see a straight line over here, which means that only the bandwidth has improved, but the latency has never improved. And that is the same case, because if you're talking about disk, it's going to rotate at a particular speed, and then it's going to and you can fetch a limited amount of data. But if you increase the platters in your disk, you can fetch more data. So again, the speed and in taking an individual task is still going to take the same time, but what you're doing, so you're not changing any latency over here, but the performance can still be improved if you add more platters to it, and that's going to improve the bandwidth. The same you can see here for networks. So again, for networks, you are going to see that the latency has not improved. It has improved because again, it's a log graph. It's going from 100 at this point, and here is going to 100,000, right? So you can see there is more improvement in the bandwidth of networks than the latency of the individual task, right? And the same goes for microprocessors. So when you're talking about microprocessors, they can be two ways to improve performance. Either you improve the performance of an individual microprocessor, or you apply some kind of techniques where you can have multiple processors working together to solve that task. So you're going to see that in microprocessors, again, there is something like 10,000 to 25,000 improvement from this is a comparison of starting from 1978 from VEX computers. So if you compare it from the VEX computer 1978 till now, you're going to see that the performance in throughput has improved 100,000 times to 25,000 times. So that's a very big number. And if you're talking about the latency here, you're going to see that the latency of these tasks has improved just 30 to 80% of the time. So what is the meaning of that is that the individual steps that are required for doing some things, like for example, addition, subtraction, if you improve that process and the individual task happens quicker, it's going to improve the latency. So the latency has improved, but it's a very small rate than the bandwidth or the amount of tasks that the processor can complete. And this is how the performance can improve. So this graph here shows how these two figures, how these two terms are related to each other. And you're going to see very easily here that the bandwidth is much easier to improve in both processors and memory disks than the latency. So you can see there is only a 6 to 8 times improvement in the memory disk from that time till today. So that's because you have to run the disk at a particular speed. You can get the data at a particular speed. But if you if you increase the number of platters, you can get much more data, and so your rate is going to increase, and that's how you're going to get better performance, right? So this is a graph showing you a comparison between the throughput and latency, right? Any questions here? Yes, anyone? Okay, so I'll just.
No, sir.
Okay, thank you. Right. So I'm just going through these terms here. What are the different terms like transistors? If you're talking about transistors, we have talked about IC technology. So if you're talking about transistors and wiring, the interconnects, so there is a term called feature size, which is the minimum size of a transistor or wire in either X or Y dimension. So that feature size in 1971 was about 10 microns, which has now in 2019, we have commercial applications, commercial chips of 7 nanometer, which is 0.007 of microns. And the work is under development for 5 nanometer technology, which is the next target for 2020. And they are available as well. So when you are going to decrease the feature size, what happens is there are different things coming in. Wait a minute, let me just share. Okay, so I'll just open. Okay, so this tool here is an equivalent of the board. I'll try to share this. Okay, so when you're talking about okay, so when you're talking about this over here, right? So when you're talking about interconnects, so it's something like, right? I cannot draw it very good over here. Okay, let me just do it once more. Okay, let me just try it once more. Okay, so we have a 3D structure, and right, something like this, and we have wires going in parallel to each other. Now, if we shrink the sizes of these X and Y dimensions here, if you shrink the size, right? So if in order to compensate that shrink, because if you're going to shrink it too much, so the conductivity is going to reduce, and in order to improve that conductivity, what you do is you make them longer. You make them longer in the Z dimension. So what happens is, since these two interconnects are facing each other, so there is some capacitance in between them as well. So we call that as coupling capacitance. So what happens is, if you're going to reduce that size, you compensate the conductivity by increasing their lengths, and then the capacitance increases also. So this coupling capacitance obviously is going to increase if their lengths are going to increase. So this is one big problem here, that if you do that, then it's going to create more issues here. So I'll just present my screen. Because I'll come back to my lecture here. Okay, so what we were discussing was about feature sizes. So what happens is, when the density of transistor increases, So when you decrease the feature sizes, the density of transistor increases quadratically. So it's not twice. It's the power of two, right? Quadratically means power of two by the power of two, right? So the density increases by a power of two. That is, you can fit more transistors on that chip, right? By decreasing the feature size. A linear decrease in feature size is going to have not two times, by the power of two effect on the density. But what happens is that the performance improves only linearly by linear decrease in the feature size. So the performance, or in terms that you can talk about that, the improvement that you are going to get in the speed of the transistor, it's only going to improve linearly. But transistors are just one element, and they are interconnects as well. So but when you're talking about interconnects, by reducing the feature size, the delays of the interconnects increase. That is because of the per unit length resistance. So you're going to see that the delays of these interconnects are going to increase, which is the main problem these days. That the transistors have improved a lot, but the interconnects that are going to connect these transistors are going very slow. So they are the main problems or delay causing elements in the chip. So feature size has its benefit as well, and the delay is going to. This is because when you're going to reduce the size of wire, it conductivity also reduces, and then um, you cannot have the same performance, right? So this was about transistors and wires. So I'll take a short break, right? So if it's okay for all of you, because I cannot obviously, and you cannot also take a 3 hour lecture. I'll see how long can we go. It's obviously very difficult to have a 3 hour continuous lecture, online lecture, especially. It's okay for the class because we interact and we have different. Yeah, we can have a namaz break here. So I'm going to come till 7:40. So we are going to join through that same link till 7:40. Okay. So is that okay with you? Okay. So I'm going to join at 7:40.